So, hello, hello. I'm just hello. Am I audible? Yeah. So I think we can start. So I am sorry for late today, and I am bit unprepared too because I had recently had a one submission for my conference. Let's just start. So do you have any doubt from previous session? Anyone, like you can raise your hand or whatever way you are comfortable. So let's just be keep this session as informal as possible, so that like we don't have any, because there are very limited people are joining. So we can just have very information informal communication about the content which we cover in the this session. So be very frank. You can just raise the hand anytime, and you can just start speaking. And basically or you can just type in the chat, or whatever way you are comfortable with. I can answer the query in both in English and Hindi. So it should not be any problem at any stage. So, without delay, let's just get started. So, this week content was mainly the broadband impedance matching. So, basically, so you can like the match the impedance by using the multi sections and those transformer. So, this let's just solve directly a few problems. So this problem talks about design a three section Chebyshev transformer to match the 50 ohm load to a 75 ohm line with the ripple level this. Also calculate the fractional bandwidth. So basically, for the Chebyshev transformer, reflection coefficient is given by this. So you will have n reflection coefficient. Suppose you design the transformer. Let me just. So if you design the multi-section transformer, so basically, that basically you can use the so you can uh, you can use basically you can vary the length of the different transmission lines. Suppose you want to match a this line impedance to a load which, and you use a like transmission line of, let's say, length L. Then basically if you choose the length wisely, then you can match the impedance of the load. Let's say this is 50, this is, let's say, 75 ohm, and this is some random load. So basically that you can match. Also there will be multiple reflection from this line. So once the wave is reflected, so let's say the reflection coefficient is gamma L is load side and gamma S is source side. So first part of reflection, so this the let's say incoming wave is like V naught exponential of minus exponential of j omega theta j j and theta, and then when this will get reflected, it will just multiply by this times reflection coefficient times at the load, and this wave reach at this point, and it will be multiplied by this at the source end reflection time. So this again will get reflected, so this will be gamma s time. So you can write the standing wave patterns at each of the node, and basically you will reach this infinite series kind of equation. And that is basically so if you use n number of section, then you can use basically you can transform this in the Chebyshev polynomial. For here for three sections, so here the in the problem it's given as the problem is with the three section line. So we can put the corresponding n values, and we can calculate the all the coefficient, and just by for matching at the left end, basically we can calculate the angle for this. So if we match the coefficient, and we can calculate by putting the equations for this. So this is the coefficient, and we basically if we calculate the all the theta values, so basically we need to calculate the theta values, and once we find the theta values, then we can calculate uh, calculate all the gamma naught, gamma 1, and gamma 3 and gamma 2 values. So then again we will put out in that, and now we can calculate for n equals to 0 will give you the fundamental characteristics impedance, and that basically we can just put it back, and then just with this equation we can calculate the total characteristic impedance or which is required to matching. So that is the case, and for n equals to 1 and n equals to 2, we can also calculate what is the impedance required, and fractional bandwidth we can just given by this equation. Basically, that is the quality factor basically on what you are matching. So that is the total bandwidth in the frequency divided by your resonance frequency, and it's basically equals to given by 4 times theta m by pi. So we can put theta m we find out, and pi we know, and we can put plug in the values, and we can get the fractional bandwidth from this equation. So this was the problem about the matching transformer design. So yeah, so if you have any doubt related to this problem, you can ask. Okay, so so yeah, so now if you don't have any doubt, so let's just move to the problem few problems related to last the assignment which was shared last year. So so let's just solve one by one all the problems. So this is the first problems talks about like which of the following statement is true for this. The section transformers used for narrowband impedance matching, and multi-section transformers is used for broadband impedance matching. So which one is true? Yeah. So as you can see, like the for single band transmission, like single section transformer, you have only one part of or one piece of transmission line inserted in between your source and load. So basically that has a characteristic impedance at only 2 points, so it will not have multiple reflections in between the lines. So this the wavelength corresponding to this line is fixed basically. So this you can use only for very narrow band impedance matching, not in the wide band case. But for multi-section transmission line, you can have for the impedance is basically is a function of theta or n, and you can use the multi-section transmission line for both for both broadband impedance matching. So the correct answer based on that is uh, both options are correct. So the correct option based on this are both first and seconds are true. So, if you have any doubt related to this problem, you can ask. Otherwise, we will move further. So, if there is no doubt, let's just move to next problem. So, in the figure shown below point, A and B are equidistant from the central of from the origin of gamma plane. So, basically, these points are this point the origin of these are the gamma plane circle. If you draw, these are the gamma circle or VSWR circle, you can say. So you can write like gamma as equals to ZL minus Z naught divided by ZL plus Z naught, and you can define VSWR uh, equals to 1 plus gamma divided by 1 minus gamma. So that basically you can with the constant reflection coefficient, you can draw the constant VSWR circle also. And then in this problem, the two A and B equidistant points are given from in the gamma plane, which can be joined by the straight line passing through the origin. If the impedance of the if at point A is 0.5 plus j times zero point 0.5, what is the impedance corresponding to to uh, to the point and this point? So basically this, if you take the uh, if you take the mirror image about this point, so basically so this, as you can see, like this distance is just wait. So if this point is so you can calculate what on the like the capacitance on reactance circle, it will cut, and what on the impedance and that circle it will cut. So basically this this point is r equals to zero point 0.5, and the reactant acts is a zero point 0.5. So basically like when you take the mirror image, that will convert to the admittance circle. So in this case actually so this the mirror image point is same points corresponding to at like the y chart. So if we draw the y chart, then this point will intersect the y point, and basically resistance we can just take the inverse of that point. And basically this if you transform that point, and you will find that your resistance at the resistance circle, it will hit the 1n minus j time point, because if this side is plus j point 0.5, then other side will be minus sign. So, so the correct answer will be will be the third one, because the this plus j is for the upper half compared to the real part of gamma, and minus so the minus j is corresponding to the bottom half, and the zero point 0.5 and zero point 0.5 will not correct, because here it's the impedance will get double compared to the earlier case if you take mirror image. So the correct answer will be 1 minus j. So that is the uh, correct impedance. So now consider the now let's just move to next problem. So uh, you have any doubt related to this problem, right? Hello, am I audible? I think you are not audible. Just wait. Uh, just uh, hello. Uh, After you were asking something, right? Okay, fine. Okay, fine. Yeah. So let's just move to next problem. So yeah, so let's just move to next problem. So consider the following circuit. So what will be the what will be the impedance corresponding to what will be the impedance corresponding to corresponding to this point. So so this so basically these are basically two section lines. So one is your this is the quarter wave transformer line, and basically and this this is the quarter wave section, and you can write the impedance as this. The if you this has this is the load impedance, which is 200. So basically you can write as just wait. So so this is a quarter wave line. So basically you can write a Z in at this point. So the ZL is given. So this will be given as Z naught square, which is the characteristic impedance of this line, times ZL divided by ZL. So that you can transform the load. So basically or you can just drive by uh, just so yeah this basically so you can write as this z naught square divided by 2. ZL. So Z naught square, if you take 100 into 100 divide by 200. So divide by 200. So it will become cancel. So this Z1 will be equals to 50 ohm. So now the this line uh, now you can write as so this is so you can transform this let's say so now any line impedance you can write as Z in equals to basically equals to Z1 times, which is the characteristic impedance of this line, RL, which is the load resistance, plus J times Z1 10 of beta L, and which this is for loss line line. So Z1 divided by Z1 plus J times RL 10 of beta L. So this, if you can, so beta L you can write beta is equals to 2 pi by lambda, and this is equals to 0.75 multiplied by lambda. So this will become so 7.5 is become 4. So it will become this will become 2 pi multiplied by lambda will get cancelled. So 2 pi multiplied by 75 by 100, and which will be equals to 3 by 4. So this will become 6 pi by 4, and this you can write as 2 pi minus pi by 4. So this you can write this if you want to transform, then basically it will transform into Z1 plus multiply by RL plus Z in 10 of 2 pi minus pi by 4 divided by Z1 plus J times RL 10 of 2 pi minus pi by 4. So now basically so now you can just you can so now basically you can write this. So 2 pi minus pi by 4 you can write 10 minus pi by 4. So it will become Z1 uh, times R. So Z1 plus this will become RL plus J times minus J times Z1, and this will become 2 pi minus pi by 4. It will become 10 minus pi by 4, and similarly here also it will become uh, this will become Z1 plus J times RL. And if you see this will similar to transform to the quarter wave transformer only. So, so if you transform this 50 ohm impedance, so that will be equals to Z naught 1 square divided by your ZL, which is 50 ohm, and which will be equals to 50 times 50 divided by 50. And this 50 will get cancelled. So the correct impedance at the input will be oh sorry, I think I lost the connection in between. So yeah. Yeah, so it will become so it will become uh, it will become this so basically so now like the input impedance will transform to the like the input impedance will be matched to the corresponding to your impedance. Yeah. So then basically the total impedance will be around the 50 ohm. The correct answer first and second and fourth answers are wrong. The correct impedance is equals to the 50 ohm. So next problem we can so is there any doubt up to now? Is there any doubt related to any problems up to now? Okay, so so if you have any doubt, just ask in between. So yeah, so this time let's just move to. If you don't have any doubt, let's just move to next problem. Design a single section quarter wave transformer to match a 10 ohm load to a 50 ohm transmission line at the 3 gigahertz. Determine the percentage bandwidth between design a percentage bandwidth between the between uh, uh, percentage bandwidth for which VSWR is uh, is 1.5. So basically, the way which we can attempt this problem. Yeah, someone raised a hand. Anand, yeah. So you have any doubt? Your voice is not audible to me. I don't know somehow this. Uh, yeah, yeah. Now you are audible. Yeah. Mm-hmm. Mm-hmm. Yeah, yeah, yeah. I will upload. Yeah. Sorry, I did not upload last week, but periodically, regularly, I will upload this video. No, no. This is second session, na? So I think is it? Oh, this is. Oh, today's. So it should suppose to start from. So it should not supposed to start from last week. Oh, okay. Oh, okay. So then I think what I am well, actually sorry, I just missed. Like I thought, like because the sheet which was shared to us, it was supposed to like the session was supposed to start on like 20th. So my session was on 21st. So I thought like the today will be the second session. Okay. So, so then I think I should cover the last week content which I discussed in the previous week. So, let me. Last week. That's why I was a bit surprised that no one joined last week actually. So, yeah. So I last week I like did the this sessions. So so actually last week no one joined, so that was I was bit surprised why why no one joined. So let me just okay, huh, okay, okay, yeah, yeah, sure, yeah, okay. So what is like the all of you registered for the exam? Okay, fine. Okay. So this let me just go through the last week content actually. So let me just erase the part which. So let me just. So let me just erase the whatever I discussed in class. So, yeah. Okay. So basically, let's just get started. So can anyone tell the what is the important importance of this subject, like which we are dealing? Why we need to study this subject? Okay. Yeah. Okay. Okay. Mhm. Yeah, that's you are right. So basically, so uh, so you know what are the RF frequencies? Okay. So okay. So like you can't say that RF frequency in gigahertz. Those are microwave frequencies actually. So okay. So let me just clarify. So basically, yeah, so those are RF frequencies. So basically, so the microwave frequency is the range from 1 gigahertz to 30 gigahertz. So why this like the why this importance why this subject is important actually. So what happens? Let's say you have the let's say 1 kilohertz signal. So if you have 1 kilohertz signal, so like this has a let's say frequency of 1 kilohertz, and if you consider the free space transmission, then this 1 kilohertz, if you consider calculate the wavelength corresponding to this 1 kilohertz, then you will calculate lambda equals to c by f. So c you can take 3 into 10 power 8 meter per second, and f is basically 1 kilohertz, 1 into 10 power 3 hertz. So this will come as this is per second, and second unit get cancelled. So this will come as 3 into 10 power 5 meter. So this is the wavelength of your wave which is propagating. So now let's say your circuit has some wires. So only this basically the wavelength is given by the distance which a wave propagating will repeat itself after this lambda by it will repeat after the lambda distance. So this is lambda distance. So basically, when you started from here, the wave will repeat after the lambda distance. So what happens is like if you have frequency very low, so your wavelength is much larger compared to your circuit dimensions on those. Then basically you don't need to consider this periodic variation of voltage and voltage and current. So basically, if you take this, let's say this is the wire or microstrip line or any line which is you made on some PCB or any printed circuit board. So let's say this is let's say 10 centimeter, or let's say this is 5 centimeter. Then what will happen if your frequency is one kilohertz, then your wavelength is very large, and over this distance, actually, if you apply a voltage at there, and you measuring some and this line you have used to drive some load or some resistance. So then basically, if your frequency is quite low, then basically you won't see any variation with the voltage you apply here, or any variation with the voltage you apply here, because the wavelength is much larger compared to your line length. Now let's say instead of 1 kilohertz, you started working on 10 kilohertz. Then your lambda will become 10 power 3 into 10 power 4. If you take 100 kilohertz, then lambda will become 3 into 10 power 3, which is 3 kilometers. And if you take 1000 kilohertz, which is 1 megahertz, then you calculate 3 into 10 power 8 divide by 1 into 10 power 6, and which will be equals to 3 into 10 power 2, which is equals to 300 meter. Now if you take 10 megahertz, then lambda will become 30 meter. If you take 100 megahertz, then lambda will become equals to 3 meters. And if you take 1000 megahertz, which is equals to 1 gigahertz, then your wavelength will become equals to zero point 0.3 meters. So now you see, let's say this is 5 centimeter line. So now basically, so now this is 0.3 meters. So it is equals to 30 centimeter. So you will start to see, and if you take 10 gigahertz, then it will become 3 centimeter. So if you take 10 gigahertz frequency, if you signal, if you apply to this line, basically, then basically that signal will have a periodic variation, and which leads to your the whatever the signal you want to uh, flow to the signal. There is a space dependent voltage and current variation in the along your wavelength and along your length of your connecting wires or line. So is that scale is clear why we need to study this subject. So as your frequency goes higher and higher, so basically you need to consider those variation just by just by having assuming this line as a lumped element parameter won't solve your purpose. You need to consider the distribution of your voltage, currents, and your capacitance and inductance, resistance, everything you need to consider distributed. Yeah. Voltage will not. Yeah. So then basically, if you are using high frequency, so basically your voltage and current will vary along the line. So then basically, if you choose different lengths, suppose let's say this is the wave it is traveling. So let's say this is the wave which is traveling through this line. So let me just draw it uniformly. So let's say this is the wave which is traveling to this line. So if you, let's say, change the line, let's say this. So let's say this is the voltage at this endpoint. Let's say this is VL. So now if you change the length of the line, this will become this. If you change further length of the line, this will become this. So as you can see, even if you vary the minor change in length of line, you will see a different voltage. And that if you are driving a load of like fixed resistance, that will lead to a different current actually. So depending on the distance, your like even minor change in your line length, basically your your like power transfer or the power transfer to this load will become variable. So that will lead to reflections, and those in the in case of high frequency case. So that basically now so the in the case of very low frequency signal, for like let's say you are connecting a wire to, if your wire length is not very large, then basically you can say like that my wire has this resistance and it will remain fixed irrespective of the frequency. So that basically you can just characterize the resistance just by voltage divided by current at the end point actually. So that basically, let's say this is the line, and you can just model the resistance just by a point, and basically that you don't need to consider the spatial variation of the voltage and current. But as the frequency go higher, you need to consider especially in the two wire lines. So basically now as the frequency becomes higher and higher, so basically there are two things which you need to consider. There can be like two kinds of lines. Basically, this is like one is your two wires line, which is your like the line connected with two wires. So for example, your coaxial cable line. So in the coaxial cable, there is a center conductor. Around that, it's a dielectric. So it's a loss dielectric material. So there is a center conductor. Around that, there is a low loss dielectric material, and around this, where basically it's a outer mesh kind of thing. So this you put onto the one circle, and this so this inner and outer, you apply a signal, and this basically in this two wire coaxial line, all the TEM modes exist, and that you can use for as the transmission line. But still, the you need to consider the case for by consider the case for varying the length of this varying the length of this line, and basically then basically you need to consider the the spatial variation of the voltage and current to calculate the impedance. So basically you can calculate the impedance by few different methods, and basically there are two ways. One is waveguide. So in case of waveguide, there is no two conductor presents. So yeah, I think someone raised hand. Is that, yeah? Uh-huh. Uh, hmm. Yeah. Yeah. So coaxial cable. Then yeah. The normal wire, actually, for normal wire, because see like the for high frequency, just yeah. So just wait, my screen. Yeah, you are able to see my screen, right? Yeah. So yeah, so for normal, even if you consider normal line also, like normal wire also. So For low frequency case, actually your length of wire does not matter actually, because your low frequency case, your wavelength is high. But then in the low frequency case, basically, so your like the only the series resistance of these wires is important, not the distributed capacitance and inductance which forms in this wire. So basically, like if you want to like have the transmission of this signal, basically you don't need to consider any distributed case, especially you are working with a low frequency. Even for two wire lines also you don't need to consider. But in high frequency case, even these distributed capacitance which comes, let's say you put two wires in nearby. So as you can see, the capacitance scale with 1 by j times omega c. So as you becomes like increase frequency in this capacitance will become will become this the reactive components, this due to this capacitance will become lower and lower. And that if you connect to lower capacitance in the in very in the parallel combination, basically those add up, and then basically you will have a effect of those effect actually. So then basically you need to consider the distributed variation even in any line if you are considering that the transmission. Ha ha. Okay. Ha. Ha. Yeah, so one thing like that at very low frequency, so basically your contribution of your contribution of your uh, so at the low frequency, basically if you drive the Maxwell equation, basically that if you drive the Maxwell equation, so that basically space dependent term will not come in your equations actually. So if you start driving the transmission line equation, so if your wavelength is very low, so those will become like independent of like space actually. So that's why you don't need to consider the distributed capacitance and inductance in that case. Is that answer your question? Okay. Uh, can you repeat your question here? Huh. Okay, so actually, yeah. So this, see, like the if your wavelength is very small, like wavelength is very large compared to your transmission line or like your wire length. So basically, this periodic variation of voltage and current is not there. So basically, like like the effect is basically like this periodic variation you can model by adding the distributed resistance, capacitance, and inductance value in the transmission line actually. So the fundamental thing is this variation of the voltage along the line actually. Hmm. Ha, ha. So this is the case. So for example, let's say if you are consider the case here, and if you consider the case here, let's say you are saying like let's say particular capacitance and resistance is coming, then you start calculating the voltage and current ratio. It will be different here. So that so you can say like let's say this is the voltage wave and this is let's say the current wave. So here the voltage and current, even the phase and phase is also different, magnitudes is also different. Here also like the phase is completely different and magnitude is completely different. So in these 2 points, like you can't say like that like the inductance component is dominant or capacitance is dominant. That is the variation along the line actually. You get my point, huh? What I am trying to say. So so the main modeling you need to consider, because there is a periodic variation of voltage and current wave in the along the transmission line, and that you can't forego because your line length become incomparable comparable to your voltage and current values. So yeah, so that basically then you so along the line length actually you can't define a finite impedance. Actually impedance is so for a coaxial line and the two wire line, if you take the impedance is basically the voltage of current and current and voltage of ratio of voltage and current. And if you consider the waveguides and those things, because there is no definition of finite current and those, so basically there you define the impedance and ratio of electric and magnetic field. So that and especially in those cases, basically TEM mode does not exist. So basically you need to consider the TE and TM mode, which was discussed in the great length in the lectures which of for week 1. So basically, you can go through the lecture those lectures and let me know if you have a doubt related to that in the next class. Yeah. So up to now, is there any doubt related to the content I covered? Okay. Okay. So basically, the main funda is like the this because waveguide actually actually is the common conductor is joining both the 2 points. So there the boundary conditions are such that it does not follow it does not allow the propagation of TEM mode. If you solve the boundary condition for a waveguide compared to the boundary condition for let's say coaxial cable lines or any other line, then the boundary condition or planar wave guidelines, then the boundary condition will suggest that there is a existence of not existence of TEM mode in the waveguide uh, compared to the existence of TEM mode in the coaxial line or other two wire kind of like the like the transmission line. So basically, that is related to the boundary condition. If even if you solve for let's say other line, let's say what are microstrip line kind of those has very different boundary condition compared to the so in the case of let's say microstrip line actually. So let's say in the microstrip line there is a ground plane, and on the top there is a dielectric. On the top you have the metal. So basically, this if you take like this will behave a transmission line, and this also you can model with the TM, and the TM wave propagate in these lines because these are two wire lines. One is the ground and other is other your signal wire. So similarly in the coaxial line, like your outer conductor is ground line and your inner conductor is your signal line. Yeah, all right. Huh? Yeah. So that basically now since you need to now see you, since you need to consider the periodic variation. So basically, you can represent like, let's say you are connecting a line to this. So let's say this is the length L, and this is the load, and this is the source side. So let's say you want to calculate. So now we know that there is a variation of impedance at each point of the line. So basically, if you want to calculate what is the uh, uh, variation corresponding to each line, so one thing is there, very simple case we consider. So the total impedance is basically the total voltage divided by total current. So at each point, the funda is, we need to calculate at each point what is the total voltage and what is the total current. So let's say if you are putting the wave from this side, so this will have there will be two waves. One is going to the forward direction, other is going to in the reverse direction, which is coming from the reflection actually. So we can write the total voltage is the sum of two voltage of propagation line propagation. So this is equals to V plus. This is the voltage coefficient in forward propagation direction, and the this will follow the J beta Z, plus the reflected wave will be equals to V minus time exponential of J times beta Z. Similarly, you can write the equation for current. Z equals to I plus, which is forward propagation constant, times exponential minus I times J times beta Z, minus I minus times exponential of plus I times beta Z. So this negative signs comes from the solving those. If you model the like Maxwell's equations to the current and voltage, then you will reach this is the function. So basically, the characteristic impedance Z naught at any point Z, which is a function of Z, you can define as a V of Z divided by I of Z, and that if you place these terms, and you will reach at this equation, and that basically you can write in terms of this transformer equation. So that is the equation of this input impedance transformed. Let's say some load is transformed to yeah. Someone raised the question. Yeah. Yeah, Anand. Yeah. You have doubt? Okay. Okay. Fine. Okay. Okay. Yeah. So that where this okay. So beta is your propagation constant. Beta is basically equals to, roughly you can define 2 pi by lambda, and Z is your the distance. You can consider from the source side also. You can consider from the load side also. Okay. Right. So. So beta is your just the wave propagation constant in the forward in the like basically is related to the frequency. So that one more important concept is as you can see like the this impedance as you go to this. So as you can see, like there are complex terms involved. So this impedance will be a complex function. So it will have a real and imaginary part, and those real and imaginary part basically you can represent at this like the in the in 2D you can represent. So basically so though you can represent in so for like for to represent an infinitely huge impedances, basically you need infinite impedance and impedance plane to store those values and to analyze those values. But there is a concept like Smith chart, which is a plot against real part of reflection coefficient to the real part of imaginary part of reflection coefficient. So basically, like you can map all the impedance in the G plane to the reflection coefficient plane, by this bilinear transformation if you do, and that basically all your impedance and correct impedance will lie within this circle. So and that you can just print it out, and you don't need infinite space to represent those impedance and whatever any impedance value which you have corresponding to any of the plane in this complex impedance plane. So basically, that those plane you can just represent very efficiently with gamma plane, which is the reflection coefficient plane, or you can say VSWR plane or other kind of plane. And gamma you can represent in terms of ZL and Z naught, and basically that ZL and Z naught you can map each ZL and Z naught you can map to unique point in gamma. So that is the Smith chart, and actually, there are different regions. So basically, so if you there are different kind of Smith charts are there. So one is the impedance in Smith chart. So basically, all the labels are with the impedance, and also there is a admittance in Smith chart where you represent the impedance in terms of like 1 by z kind of transformation. So like the same impedance, same complex impedance you can represent on admittance Smith chart as well as impedance is Smith chart. So this basically this so this this you can draw as like this, and this the outer so it has a circles. So this is the z equals to 0 point, and this is equals to z equals to infinite point. So basically this is known as the open, and this is known as the short, and in between basically you can draw other concentric circle. If you represent, then basically your this kind of circle you can also draw. So this and also you can at this point you can draw other circles also. So these are these circles. So this is the either reactant circle. So this is the reactant circle. So this you can drive. Actually, this is very simple derivation. So to draw the reactant circle, to do the mapping from Z to L. So basically, you need to normalize this equation, and basically to find ZL and Z naught in terms of your reflection coefficient. And basically to drive the exact equation of the Smith chart, basically this gamma is equals to ZL minus Z naught divided by ZL plus Z naught, and ZL can be any complex number. So this gamma you can represent as a real part plus I times gamma of imaginary part equals to ZL minus Z naught divided by ZL plus Z naught. So if you consider like each of the value of this, if you represent gamma real and gamma imaginary in terms of ZL and Z naught, then basically you can take ratio also. So this will become ZL by Z naught minus 1 divided by ZL plus Z naught plus 1. So basically this will become uh, this will become so you can basically and if you can represent ZL as Rx plus J times Ix. So basically Rx is the real part and Ix is the imaginary part. So this at this point will be correspond to Rx, and this point at the imaginary axis will be correspond to Ix. So this point, how you will represent in the corresponding in the gamma circle, you can just find out what is the value of corresponding to this Rx and Ix value of this, what is the value of gamma and gamma I. So that basically you can represent at this gamma plot, and then this is basically the bilinear transformation of your cycle. So as this is fine, these are the constant resistance circle. So at these circle which I have drawn, the resistance is fixed actually. So even if does not matter what is the value of what is the value of capacitance and inductance, or capacitance or admittance, there is the resistance will fix. Similarly, on this circle, the capacitance or inductance will remain fixed if you are moving along this circle. So basically, these are known as the constant reactance and constant resistance circle. Also, there is one more kind of circles are there which you draw at this center and you draw around the center. These are known as the constant reflection constant, constant gamma, or constant VSWR circle. So these are the VSWR circles. So that also you can draw with the Smith chart. So is there any doubt related to this? Mhm. हाँ 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 ओके so okay. Okay, let me just derive it actually. So that will be more clear. It will make more clear actually, right? So let's say, right. So let's say we have gamma, which is made of gamma real plus j times gamma imaginary, which is equals to, let's say, zl is equals to rx plus I times ix. I am representing, I am dividing this by Z naught to normalize with the characteristic, then divide by the R naught, and this is because it will be equals to Rx by Z naught plus J times Ix by J naught, and this quantity I am calling as small I times X, and this I am calling as R times X, right? So now, if you write this, so this the impedance which reflection coefficient at the load side you can write as ZL minus Z naught divided by ZL plus Z naught, right? So this basically you can write take Z naught as common, so it will become ZL by Z naught plus minus one divided by ZL plus Z naught plus one, ZL by Z naught plus one. Uh, yeah, right. So now ZL plus Z naught I can write as uh, so it will be equals to small rx plus j. So this I have not assumed anything. I am, because this is a complex number. I am saying this gamma r is a real part of any complex number, and gamma I is the real part of any like imaginary part of any complex number. Yeah, so that is just reflection coefficient formula. So gamma reflection coefficient, you can at the load side you can write ZL minus Z naught divided by ZL plus Z naught for any complex impedance, right? That is your fundamental relation, right? So now I just normalize it, and I am write Ri plus J times Ix minus 1 divided by Rx plus J times Ix plus 1, right? So this I can write this Rx minus 1 plus J times Ix divided by Rx plus 1 times plus j times ix. So what I will do now? Now I will make the like complex conjugate of the denominator. I will multiply so that denominator is always real. So that I will multiply rx plus 1 minus j times ix. Similarly, above also I will multiply rx plus 1 minus j times ix. So this will become at the denominator. It will become so now this at the denominator it will become so uh, this will become rx numerator rx minus 1 times rx plus 1 minus j times ix times rx minus 1 plus j times ix times rx plus 1 minus this j square will become minus 1. So this will become plus times ix square, right? So so it will become minus jx square, and j square you can write as a minus 1. Then it will become just positive ix square. Then the denominator will become rx plus 1 whole square minus j times ix whole square. You can write just a square minus b square, right? So now if we simplify, so this will become rx square minus 1, because this is a square minus b square, minus uh, j times ix rx plus j times ix. Similarly, this other terms you can write plus j times ix rx plus j times ix plus ix whole square. So as you can see, these two terms will get cancelled, and on the bottom it will become on the denominator it will become like rx plus 1 whole square plus ix whole square, right? Hello. Okay. So that basically basically now you can this term will get cancelled. So this will become 2 times ix. So this will become rx square minus 1 plus 2 times ix plus ix square, right? So this basically this is so you can write this so this will become so rx square minus 1 uh, yeah, sorry. I think yeah. So yeah, so this you can write as uh, you can write as just wait. So now basically you can write as this this you can write as just if you can represent the circle. So basically this now you can compare the real and imaginary part of gamma with this. So basically so the just wait, let me yeah. So this the real part is rx plus ix square minus 1 plus uh, 2 times 2 times I times ix divided by rx plus 1 whole square plus ix square equals to gamma r plus j times gamma I. So the gamma r is equals to rx. So rx plus ix square minus 1 divided by Rx plus 1 whole square, Rx plus 1 whole square plus Ix square. And so this you can simplify as so this you can write as so this you can so basically this you can write as so if you take here uh, so if you take 2 times Rx minus 2 times Rx, so you can and you can add plus minus 1 also. Basically, I just want to make this kind of like the I just want to simplify it such that let me just write it clearly. Yeah. So I what I will do, I will do plus and plus 1 and minus 1 here. So it won't take plus 2 times Rx minus 2 times Rx. And these terms I will combine basically these terms Rx square and this plus 1 and this 2 times Rx. This term I will take together. This will become Rx plus 1 whole square plus Ix square. So then other terms will be minus 2 minus 2 times Ix. Right? This will become Rx plus 1 whole square plus Ix square. And so this will become 1 minus uh, 2 times 1 plus Ix times Rx plus 1 whole square plus Ix square. So this basically now if you like if you can represent if you can represent like this circle basically uh, the complex impedance of this part basically you can just you can write this Ix and Rx in terms of gamma R and gamma I. So basically you just transform from like one plane to other plane actually. So then basically you see like you see the like the solution of this equation if you try to solve it at home. So basically there are two kind of circles are there. One is with the one is the this the two kind of circle will come out of this. So one has this center points like the centers vary along this line, and your and in other center vary along this line actually. So those basically this circuit corresponding to imaginary part, and this correspond to real part actually. So these are constant circle, and which one end is this, the center vary along this line actually. As you vary the reflection coefficient or you vary the load. So this is the funda of Smith chart. So is that understanding is clear, or is there any doubt? Yeah. So basic. Yeah, you reflect developed by analyzing the reflection coefficient equation. So basically, the idea is on any load with respect to your and like the because all the coaxial lines are 50 ohm line. So any load you can represent in terms of the complex reflection coefficient you can calculate. So back and forth conversion you can do. So if you know the your load impedance, you can represent that as the Smith chart, and you can get the reflection coefficient what will it will have corresponding to uh, corresponding to your your corresponding to the that line. So basically let's say you represent any load it here now. So these are the constant gamma circle. So if you represent like this, these are the this other green and red circles are resistance and resistance and that reactance circle. So basically any load you can represent in terms of resistance and reactance. So you can represent any load at the periphery of this Smith chart, and that load basically you can convert. You can once you find this point at the Smith chart, you can draw the by taking at the center, you can draw a circle that is that where it intersects the line here or where it intersects the line here correspond to the reflection coefficient actually. So that basically, if you have any load, you can calculate the reflection coefficient. And if you know the reflection coefficient, let's say complex reflection coefficient, then you can know the complex impedance also. So this back and forth converse, like uh, like uh, back and forth conversation is very easy in the Smith chart. Yeah. Hmm. Yeah. Yeah. Huh. So yes. Okay, okay. So basically, any complex reflection coefficient you can represent like this actually. So, like let me in the previous class, like previous when I delivered. So that basically reflection coefficient. So let's say so here this is so here the so basically let's say this is your generalized load impedance, right? So you can write the reflection coefficient Z gamma as equals to Z of G minus Z naught divided by Z of G plus Z naught, right? Then if you put the value of this V and I into this equation, you will reach at this point. So you will reach this equation actually. So these are coefficient, and as you can see, like the reflection coefficient basically, so as this Z is varying with the Z, so the so at the load side basically, so suppose you have connected a lossless transmission line to a load and you are moving along this line. So this suppose you know the reflection coefficient at load side, that gamma load is basically equals to Z load minus Z naught divided by Z load plus Z naught. So the at any point if you move away from the, you can drive this by yourself by this equation actually. Zn is Zl, like this is very general equation. You can drive by any point from this, and you will reach that at any point your reflection coefficient as you move along this line, let's say L, at L basically equals to the gamma at load side, which is mod times exponential of minus j times twice beta j. So basically, as you can see, like your the complex reflection coefficient is changing as you are moving along this line load from this. So, but the magnitude is same. Magnitude of the reflection coefficient is same. So that is the constant reflection coefficient circle, which is this just hold a minute. So that is basically so that basically that so this constant gamma like at this so at this center circle. So let me draw it correctly. So let's say it's if you drawn this circle and this like this the radius of this circle is mod gamma. So at each point in the circle mod gamma radius is the same. Only the like the if you consider the real and imaginary part, only this phase factor is changing actually. So this will this 2 beta z, so beta z repeat with lambda, 2 beta z will repeat at so where the 2 pi, beta z is equals to 2 pi, you can say the beta z like this, this gamma L will repeat at each lambda by 2. So basically each lambda by 2, the on the Smith chart, basically you will come to the same point actually. So is that clear? Yeah, every lambda by 2. Yeah. Yeah. Uh-huh. Yeah. 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 Hmm. So the two things you can do, you if you it's like there are different kind of things you can do. Suppose you are sitting at the fixed point and you are varying the frequency. Then also your complex impedance will change because you varying the frequency. The wavelength is varying. The beta jet component will, although Z is fixed, but beta is varying then that case. So that's why then also your complex impedance is will vary. And that experiment I do in my lab. So basically to match my impedance at the particular resonance frequency, I sweep the microwave frequency actually. And as I sweep the microwave frequency, my complex impedance will pass through like this. So if I vary the microwave frequency actually. So that this kind of plot I have actually. So in the lab kind of I don't know I can show it or not, but yeah, that kind of plot I normally use actually. So so basically, if you sweep the wavelength or frequency, then also you can move in the in the Smith chart actually. So that is the idea about the Smith chart. Let me just quickly go through the last year problems. So I think most of them can be answered with uh, very little effort. So yeah, these were quite simple problems mostly. So like this, which is the property of TEM wave, which is the transverse electromagnetic wave. So as you know, the electric and magnetic field is perpendicular to the propagation direction. So all the two wire lines or free space propagation, all the electrics and magnetic field are perpendicular to the direction of propagation. So let's say if you are considering the propagation in z direction, so basically in the ez direction, basically your electric and magnetic field magnitude amplitude will be zero. So the correct answer is ez and hz are zero in the propagation direction if you are considering z direction as the propagation. Let's say in exam someone says wave is propagating uh, in x direction, then what is the then your ex and if it is propagating in x direction, then your ez and uh, e by will not be zero, ex will be zero. So always you need to consider from the propagation direction. Is that clear? I think this will be quite simple. Yeah. Okay, so let's move to let's move to the next problem. So, which of the following mode have with a cutoff frequency other than zero? So, as you know, like the two wire transmission line, the TEM mode is broadband mode actually. All the frequency transmit. So, only which of the following have a cutoff frequency other than the zero? So, only the TEM mode will have all the broadband line. Other mode which TE and TM mode which exist in waveguide. So those waveguide modes will have a finite cutoff frequency. So that does not follow the that linear dispersion curve. The like normally in the free space transmission, your beta is directly proportional to omega, but for waveguides, beta is that not directly proportional to k it's some different function of k. It's not directly proportional to it. So all those kind of dispersion relation will have non like will not like the will have the TE and TM mode exist only in case of the uh, TEM. All the frequency will TEM mode will pass all the frequency. TE and TM mode will have non-zero cutoff frequency. So the correct answer will be the third one. So let's move to next problem. So that input impedance of a transmission line repeats after every length. So as you can see, like the uh, gamma, which is equals to ZL minus Z naught by ZL plus Z naught. As we have derived this gamma repeats every lambda by 2, which is also a function of ZL, then ZL also will repeat as a function of uh, gamma by 2. And that you can derive it also actually. So you can write Z of any point L is equals to V plus exponential of minus J times beta L plus uh, V minus exponential of minus V minus exponential of uh, uh, j times beta L. Similarly, you can write I plus times exponential of minus j times beta L minus I minus exponential of plus j times beta L. So now if you take minus beta L turns common minus beta L times V plus from the numerator. So V plus, so this will be V plus exponential of minus j times beta L. This will become 1 plus V minus divided by V plus, and this will become exponential of j times 2 beta L. Similarly, this will become v minus, this will become I plus exponential of minus j times beta L. This will become 1 minus I minus divided by I plus exponential of j times beta L. And this you can define as the reflection coefficient, that basically you can write in terms of like this is this beta L term will get cancelled, and v plus and v minus is your, like, if there is no reflection, if reflection terms is zero, then basically you will have impedance that is your characteristic impedance, that is Z naught, and that you can define 1 plus gamma divided by 1 minus gamma, and you can write so this is Z, you can write Z by Z naught equals to 1 plus gamma divided by 1 minus gamma, and if you reach out this and this, you will find that gamma equals to Z minus Z naught divided by Z plus Z. So that is the funda behind here. So this is because this contains 2 beta L term, so it will also repeat in lambda by 2. So the correct answer is lambda by 2. Is that clear, right? I am maybe going a bit fast because I think we are reaching maybe in that yeah. Is that clear? Is there any doubt up to now? Okay, fine. Okay. Yeah, just after this session, this session I will. So that the waveguide is the next problem is waveguide is low pass, band pass, high pass. So waveguide has a, as you can see, like this has a dispersion relation which has a cutoff frequency like this. So this is the linear dispersion, and waveguide will have the dispersion like this. So it will have a this is omega and this is beta. So the beta will become constant as you become a lower and lower frequency. So it will not it will not have a linear dispersion. So it will not pass the lower cutoff frequency. It will pass the higher cutoff frequency actually. So for lower cutoff frequency, it will reject, and that it will behave as a high pass filter. Actually. So with this, let's move to next problem. In a non-dispersive media, we are moving away from the load. So non-dispersive media means lossless. So all the transmission line or medium which does not cause any loss, as we are moving away from the load, the magnitude value will be for the lossless line. The reflection coefficient is remain constant. Actually, if you can see, like this term will come as a only the phase term will be varying with the is a function of distance. These are the constant actually. So this phase term does not, as you take the magnitude, this phase term will go away, and you will have only the magnitude will there. So the reflection coefficient will remain the constant. So uh, uh, with that, let's move to next problem. The larger the standing wave ratio, larger the maximum voltage and minimum the voltage. So uh, voltage standing wave ratio VSWR is basically uh, related to Vmax divide plus Vmin divided by Vmax minus Vmin. So if you take Vmin as a constant, so it is it's like the larger the VSWR if you achieve if you have Vmin is very low and Vmax is high. So the first statement says larger the standing wave ratio, larger the maximum voltage and lower the minimum voltage. And larger the standing wave ratio means there is the perfect matching between the impedance and load impedance. So standing wave ratio, if you calculate, so it will be VSWR will be equals to V plus by V minus divided by 1 plus gamma divided by 1 minus gamma. So if you have reflection coefficient as, let's say, a very high reflection coefficient, then basically the reflection coefficient, if it is equal to 1, then basically this term will become denominator will become very high, and denominator will become 0, and your VSWR will become equals to high. And if this gamma will tends to 0, then basically your VSWR tends to 0. So if you have less reflection, then your VSWR tends to 1, and that the second statement is false. So the correct answer is first statement is true and the second statement is false. So this is the correct statement. So uh, yeah, so let's move to next problem. In a transmission line, voltage at any point proportional to sum of two voltage waves. That is correct. Current at any point is proportional to the sum of two voltage waves. Current is not proportional to two voltage wave sum, but is a difference. Current at any point is proportional to the difference of the two voltage wave. So the correct answer is A and D. And basically, you can, as you can see from this equation, you can drive this even in the class. Yeah. So with the next problem, let's move to next problem. Is the omega is equal to beta times C plus alpha, where C and alphas are constant. Then basically group velocity omega Vg, you can calculate d omega by d beta, and if you take derivative with respect to beta, this will become C. The group velocity is constant, and the phase velocity is not constant. So so the phase velocity Vp is equal to omega by beta, and which is not equals to C plus alpha by beta, and which is not constant actually. So the correct answer is group velocity is constant and phase velocity is not constant. Other options are wrong. These are wrong. So with the next problem, a transmission line with the characteristic impedance Z not be terminated with load impedance RL. If the length of line is a lambda by 4, then a load impedance uh, and the load impedance RL is infinity, then input impedance is. So basically, this is the case of quarter wave transformer. So Z input impedance is Z naught square divided by ZL. So if you correspond ZL is infinity, then your input impedance will tends to zero. So the correct answer will be D1. And you can derive this by this generalized equation also. So that let's move to the last problem. Which of the following is are true of the Smith chart? That can be used for impedance matching. That is correct. Finding the load reflection coefficient if the load impedance is given. That is also correct. Finding the load impedance is load reflection is also given. If you are giving the reflection, like you can plot any point with the reflection coefficient, then corresponding you can find the load impedance also. So that is also correct. And if you know the reflection coefficient, you can find the VSWR also. That is also correct. So all of the options are correct actually. So any point conversion is very easy in the Smith chart. So these are the problems for week one lecture series. So if you have any doubt related to these problems, you can go through the video I will upload in like just after this. So then if you have any doubt related to the content I presented today, you can ask, or we can end this session and meet next week. Yeah. So if you have any doubt, you can ask, or otherwise we will just end this session for today. Okay, so if there is no further doubt today, so let's just end this session. And oh, okay, so yeah, someone has a doubt. Yeah, after you have a doubt, right? Uh-huh. At what location impedance matching is take place? Okay, so basically, as you can see, like the uh, this this like let's say, let me draw it clearly. So yeah, yeah. So this is the chart. So if you draw if you draw this circle, then this is gamma equals to one circle which has the highest reflection, and at the center it is the gamma equals to 0 point. And in between that gamma it is between 0 and 1. So the impedance matching is at the center point actually. So any load impedance, if you want to match, let's say it's there. So the reflection coefficient, if you draw a concentric circle by taking this much radius, then basically that is your reflection coefficient where this intersect line here, and that scale you can read and you can calculate the reflection coefficient. So basically, to match this line, to match this, basically this point you need to transfer to the center of the Smith chart. Actually. So any point you need to transfer to the center of the Smith chart to match the impedance. It's the gamma real and gamma imaginary equals to 0. Yeah, yeah. So the center of this the constant gamma circle, center of the Smith chart, you can say. Okay, fine. So then we can end this session for today. We will meet next. We will meet uh, next time in the same slot next week. Okay. Okay, fine. Till then, time. Thank you so much, and we will meet next time in the same slot. Bye. Have a nice time and a good night. Yeah.